We have two sessions here, really. One is this morning, which is sort of like more or less presenting what we're doing, and this afternoon is going to be sort of more commentary. However, we would like to make sure that we entertain questions this morning. And the primary thing this morning is going to be Eric Schneider is going to give a full kind of presentation outlining the themes of the Into the Cool, I like to call it research program. And then he'll take questions, and then depending on the time and how we go, Dorian will do something, and maybe I'll do a couple of comments if we want to have some questions and dialogues. And then this afternoon at 1:30, right? 1:30 is our second session. We'll do a little bit more. I will then do a little bit on kind of framing the issues that I see, which I call the engineering perspective, which is just sort of saying, looking at things from a classical thermodynamic point of view, but really taking the engineering, history of engineering and those concepts seriously as applied to understanding evolution. We sort of think we're all in the same arena here, but it doesn't mean we all agree. So Dorian has things to say that I may agree with Eric, but we're this sort of loose team of explorers into some new territory here, a new way of thinking. So with that, Eric Schneider got his PhD in oceanography from Columbia, and he was for a period the chief scientist at NOAA. So he's a very impressive guy, and he has, I'm just going to give it to you. Go for it. You're hit.
Writing this book, Into the Cool, was a 12-year project with Dorian and myself. It was truly a collaborative project. Both of us equally wrote this book, came up with the ideas, and put it together. I got into this by directing the laboratory for the Environmental Protection Agency. It's told to protect coastal waters in the ocean, and found out rather early that there was, in 1972, really no theoretical underpinnings for ecology. There were no ethical MAs, there were no Navier-Stokes equations, so I decided to get into the business of trying to find out where were the underpinnings for ecology and somewhat theoretical biology. The first person I turned to, because I had a physical background, was Erwin Schrödinger. We all know that he won the Nobel Prize for his work in wave mechanics. What we don't know, most people don't know, is right before World War II, he escaped Graz, Austria, leaving his Nobel Prize medal and his paper chains on his kitchen table. Got out on the last train, made his way to Rome, stayed in the papal residencies for a few weeks, made it to Cambridge, and then finally to Dublin. There he hung out with writers, painters, actually found himself quite happy painting scenery for plays. Got bored after a while and decided to give a few lectures, and his lectures that he gave later turned into a 91-page book called What is Life? The Physical Aspect of the Living Cell. What he extracted from his view of biology were two things. One, order from order, the gene with its living process, the DNA from its and its RNA. He was a decade ahead of Watson and Crick, but he did recognize that there was some process in order in biology that produced order from order, the parent from this project. He realized, and he had friends who worked in the forefront of biology. He'd seen, and his friends had shown him X-rays that showed there was a helix, and he knew the packing density of this helix, but he didn't know much more than that. But if you read the book, or if you haven't, you'll be rather amazed at what he knew about DNA at that time. The next thing in the latter third of the book, which has basically been like a tell you some amazing stories about this, didn't discard it and not pay any attention to, was his order from disorder. And this is non-equilibrium thermodynamics and self-organization. Very few of us have run up this path. And as we know, his order from order has turned into a $1 trillion research program and has given much to his society. His order from order processes, no one has paid much attention to, and in this, he asks questions of how come something like the magnificence of a tree form order from disorder. How can molecules like oxygen, nitrogen, and phosphorus, and water, almost invisible things, give rise to highly ordered things like trees? And he went in at some length and talked about there was going to be a new field, and he used the word non-equilibrium thermodynamics, and there was no field that even existed at that time. The philosopher C.P., now we're talking about thermodynamics. C.P. Sills said that the second law of thermodynamics was not like not knowing it was like not having read the work of Shakespeare. So when I give this talk in bookstores, there's quite a chuckle when I say this, but I say at the end of the lecture, you're going to notice and you'll be one up on your literary friends. What is thermodynamics? And Dorian is going to talk and give a paper out, or maybe he's already passed it out on the word entropy, and it gives some real clarity to that word. But there's a bunch of complicated words like exergy, entropy. I got this off a bathroom wall at Woods Hall, tied a yellow ribbon around the entropy. Really get it. The second law of thermodynamics. So far, it's among the most inviolate laws of nature. It holds from quantum scales to black holes. And a easy form is nothing in nature is free. We'll talk about this a little later. There is no such thing as a perpetual motion machine. There is no free lunch. Dorian and I have simplified this, but others have done it ahead of us with much mathematics and very well put together. The second law of thermodynamics can really be simplified to the statement of nature abhors a gradient. What do we mean here? First, let's talk about gradients. And I have it in little letters up here, but I'll read it for you because it's very, very important. We have to say what a gradient is. A gradient is a difference across a distance. We can have temperature gradients, pressure gradients, chemical gradients, electromagnetic gradients, gravity gradients. Let's just talk about the top ones first. A temperature gradient. Cold glass of water with ice in it, leave it in the room, come up in the morning, it's the same temperature. It's gotten rid of that gradient. Nature has gotten rid of it. It abhors that gradient. Okay? That's thermodynamics. Pressure gradient, yellow pinhole leaking your tire. There's a difference across the distance between the pressure gradient in your tire and the outside. It comes down as flat. Second law of thermodynamics. All of physical chemistry is chemical gradients, electromagnetic gradients. I won't go into that. The last two I have here are economic gradients and social gradients. Some scientists in the room may want to really argue about that last two, but many of my social friends like me to include those. And that's an area of work where I think there will be some progress in the next 50 years. Okay, what falls out of nature abhors a gradient? Okay, one is thermodynamics seems to be the only science in which time really is given some scientific significance. Time in its direction. Okay? Before thermodynamics came along, it was hard billiard balls that bounced around. Irreversibility falls out of the second law of thermodynamics. And it's a key thing in nature as we'll see it. The next thing is systems will go to equilibrium if possible. Not only gravity does this, but the second law does this. We'll see later that work can be extracted from systems as they go to equilibrium. We've got little motors here, we'll show you that. And that systems, and I left the last little part off of this, is systems can be moved away from equilibrium if energy is put behind them. We'll give you an example of that. Okay, let's teach you the second law of thermodynamics. Here's an ice tray in which I have a whole mess of molecules that are bouncing around in the upper left-hand corner. Now, if I open up little gates, here's my little over here. If I open up little gates between these doors, and these are hot molecules bouncing around as fast as they can, and then I shake this thing, and they become evenly distributed. Now, if I had a little oxygen container up in the corner of the room here, and I open the valve, and they, within, say, an hour, all those oxygen molecules, I don't have to shake them in this case, will be equally distributed among the room. In this case, it's hot molecules being moved around and being equally distributed among the room. Now, as hard as I might want it to be, the oxygen molecules in this room will not all accumulate in this upper corner and we would not asphyxiate. Okay? This is the second law of thermodynamics as described by Boltzmann. You notice everything here takes place in a closed little box. Now, lots of people have tried to get around the second law. And this is an example that's been put forward by a lot of people called Maxwell's demon. Here we have hot molecules and cold molecules. The cold in the little round circles and the hot molecules here. Maxwell said if I could make a little deft, energy-free demon that could identify the hot molecules and the cold molecules, and he could lift up a trapdoor, he could separate these two sets of molecules. And then he'd have a gradient between the hot molecules and the cold molecules. And if you wanted to build a perpetual motion machine, you could, with this little guy, separate these two things, put a tiny little hole in here, put a pinwheel in here, and as they did like my previous slide, came back to equilibrium, I could generate energy and have a perpetual motion machine with my little Maxwell's demon. Everybody has tried to build one of these things in computers, in their mind, but not any time. Finally tried to do this and found the damn thing would shake around so much so that it would never work. So this is probably one of the, and everybody's tried this to make a Maxwell's demon in their minds and computers, and it never happened. So this is probably the best example of someone trying to break the second law. As I said before in one of the earlier slides, it seems to be one of the most inviolate laws in nature. And this is one of the best examples of trying to break it. Okay, I've been lying to you up to now. A branch of thermodynamics that has not been well explained to the public, and this is so-called non-equilibrium thermodynamics. And this is what I've spent the last 30 years studying. These are systems that are not in boxes. These are systems that are open to energy and to matter. These have gradients across their boundaries. These systems are able to degrade or dissipate energy, and they're irreversible. Once I open up the boxes, I can't get it back in. These systems have nonlinear interactions. The mathematics of them are very, very difficult. And even the simplest systems are very, and those of you who worked in nonlinear systems know this, are very, very difficult to model. Systems are non-decomposable. The systems are more than the sum of the parts. They're hierarchical, or part of a nested system. And I won't go ahead and give you examples of this, but you know them if you worked in science. All of them have cycling. Harold Marowitz actually says that cycling perhaps should be the fourth law of thermodynamics. All these systems show cycling. These systems exhibit catastrophic behavior. And those of you, luckily I'm not in a bookstore, I'm in with a group of fellow scientists. We know there's a whole field of mathematics dealing with catastrophic behavior. These things show organized. We don't know if they're self-organized, but they show highly organized behavior we're going to show. These things show internal causality, goals, and feedback. Our past president of this organization worked in this area. When I say this, just look at this, internal causality, and I'll just give you the simplest example. I'm going to be in internal causality. I see this, I'm going to pick this up, okay? Internal causality. I have a goal, which is to pick this thing up. I have feedback, I'm going to put it back down, okay? As later we're going to see with Schrodinger, he says, if I can do this, I am God Almighty. I'm moving atoms and molecules, okay? This is a pretty interesting thing that I got here because I have internal causality, goals, and feedback. Read Schrodinger's book, What is Life? It's only 91 pages. The last 4 pages talk about these types of issues in science. His initial publisher wouldn't publish the book. Cahill Publishers in Ireland wouldn't publish because he put these subjective thoughts in this book. And when he didn't do it, he sent it off to Cambridge University Press and it was published immediately in a less secular state. So this is the fun. This is, if I were a graduate student, I would get into this area. This is where science takes place. These are clouds, these are rivers, these are human beings, these are birds and rats. Most all the systems that a lot of systems we look at are equilibrium. Many of the systems we look at are returning to equilibrium. In much of undergraduate chemistry, you mix this, you mix that, and they come to equilibrium and you get that. Many of the systems in real nature are non-equilibrium systems. This is a simple one I picked, which was the beach ball being blown up in the air at the appliance store by a vacuum cleaner exhaust. And it bounces around. You really couldn't mathematically describe where it's going to go next, except if you turn off the exhaust, it'll return to equilibrium and come down. Okay? So this is a non-equilibrium system, and this is the simplest one that I can think of. We can go on and look at all the other non-equilibrium systems, but basically everything in the world is non-equilibrium. Now we're going to look at a couple non-equilibrium systems. Okay, this is an open system. In this case, I have a hot source, I have a thin layer of oil, and I have a cold sink on top. This is called a Bernard cell. I should have a little inflection here because it was a Frenchman. Bernard. This is called as well. Because it's hot underneath and cold on top, the hot molecules rise, they cool, and they go to the bottom. Little convection cell. Actually a little complicated than that because it's in surface tension with all rooms. Okay, let's look at the convection cells. This is macroscopic. This is a Petri dish. Okay? Little perfect pentagonal, perfect hexagonal cells. Hexagonal. Highly organized, self-organized systems. These are macroscopic. We can see these. We don't need a microscope. There's no biology involved in this. There's no chemistry involved in this. Okay? This is self-organization involved. Okay? This is thermodynamics. Breaking down a gradient. You're going to see this time and time again. I'm going to drill this into your head. Thermodynamics and self-organization, where there is a gradient and constraints are right, you can break down, you get self-organized system. There's another system. And now we're going to deal with a pressure gradient. That was a temperature gradient. Here we have a little system which is 2 cylinders, an outer cylinder and an inner cylinder. We put, in this particular case, is silicone oil with a little bit of aluminum, so we can shine a light on it, see what's happening inside there. We twist this, and a pressure gradient sets up inside this thing. Forces. And as this sets up, amazing little organized system. Look at that. No biology, no chemistry, just a pressure gradient across this, okay? We're breaking down a gradient and getting a highly organized system. We did it with temperature, now we're doing it with pressure gradients. Gradients being broken down, organized systems emerge under the right constraints. Okay, here we have a hurricane. Warm seawater temperature, cold upper atmosphere, and then emerging out of that is another pressure gradient, which drives the winds. Now, everybody all summer long heard a lot about hurricanes. Heard, the warm sea surface temperature in the Gulf of Mexico is driving us crazy with all these hurricanes. But no one ever said anything about the cold upper atmosphere. And what was really running this thing was a giant temperature gradient, a heat engine. I wrote 3 letters to New York Times science section and saying, hey guys, why don't you mention the cold upper atmosphere? Even sent them a PDF file of this whole thing. And they refused to print. And they said, we've written too many articles about hurricanes already. And I said, hey, no one understands these things, guys. You talk about the warm seawater, but you never mention any of this, okay? No one understands hurricanes. I put this up for 2 reasons, okay? The higher the wind speed, and this is the pressure gradient. This is the gradient between the outside of the hurricane, and the inside of the hurricane. And the higher the gradient, the higher the wind. The only reason I put it up, this little thing, Roma, that came through, bottom right up here. And this is 100 years worth of data, and needless to say, those are all the points. But it was a very rare storm that came through last night. Okay, now we have pressure gradients, temperature gradients. Let's deal with chemical gradients. This is called the Belly-Lutzow-Zagotinsky reaction. It's a cerium oxidation reduction reaction. In this case, they put the appropriate chemical in the petri dish. Again, all these are macroscopic. See these with your eyes. They put a drop of the appropriate chemical in the petri dish, and these spiral waves emerge. Okay? Again, a gradient between one form of chemical and another form of chemical, and you get these self-organizing macroscopic patterns. Again, millions upon millions of molecules all lining up in a macroscopic pattern of gradient and self-organization takes place. Now, a colleague of mine, Joe Early, from Georgetown University, which is a Jesuit school, had a laboratory tray with 4 of these reactions going on, and he was coming out of the classroom, going to the elevator to take them back to the laboratory. And some of these actually pulsate, some of them do this. These things were pulsating on the table, and 2 Jesuit priests came up and looked at these things and were just fixated by them. And they said, Professor Early, are these live? And he had a quick line that he said, really no more than you, Father. They metabolize, but they don't reproduce. Okay, now let's look at another form of greenhouse. Okay, here we have the cold outer space. And to make it simple, we'll say it's 3 degrees K. Here is the sun at about 6,000 degrees K. And here's the poor little Earth caught between this gradient of 6,000 and this gradient of 3 degrees K. Okay, what happens when we put this a system in this gradient? This is haplessly caught there. 90% of the energy in the system sits and runs our weather and our ocean current systems, about 90%. Lots of, the energy budget of the Earth is a complicated thing. Sun's reflected, but roughly 10% is left to run biology. And let's look at this a little more. I use 6,000, the right term is 5,800 K. The temperature of the Earth is roughly 280 K temperature of the universe. So we have hot photons coming in, cold photons coming out. The Earth is degrading the gradient, okay? Because this real hot stuff comes in and cold stuff comes out. And now let's see what happens when we do that. Okay, we have ecosystems. And in this particular case, and many of us know this, is we have the sun. The first thing that comes in and gets involved in this is the primary productivity level. This is photosynthesis, we'll look at this later. Because I live in Montana, my artist drew things like elk and the herbivores that eat our grasses and trees and things of this sort. But if I'm from the ocean area, instead of having trees, we have plankton, and instead of herbivores, here we have zooplankton, and instead of our herbivores here also might be whales. But finally we get up the trophic level and we run into coyotes, badgers, and bears. And this has its own trophic levels, things eat things. It's difficult to put a whole number on these trophic levels. Most people think trophic levels are even numbers. They quite frankly are not. Just take the bear. The bear eats twigs and leaves. The bear eats herbivores. The bear eats sometimes man. A colleague in Montana State says he's seen feces contain an oil filter. So you can't put it at simple trophic. So what I want to say is trophic levels aren't even numbers. Ecosystems are systems of organisms acting with others in their environment. That's the simple thing you find in those textbooks. However, ecosystems are not just things out there in the environment, but comprised of processes that make up nature. So if we think of ecosystems as processes, and we'll look at that, you and I are not things, we are processes. We're full of organisms that are carrying out processes and that are interconnected within us. Think systems and processes rather than things. Ecosystems are found everywhere and all over nature. They're under our fingernails. They're in mud puddles in the street. They're in meteorites that come in from space sometimes. Okay? There's life on some of them. So ecosystems are ubiquitous wherever we look. Well, now we're going to look at something that's one of the most ubiquitous things in nature, which is succession. Now, in this case, we had a fire. Okay? And now we have grasslands that start to move in, shrubs, pine forests, larger trees start to grow, and finally at the end we have several things that can happen. It can go for a very long time. These ecosystems can go for 1,000 years until something happens like a fire at the climax forest. Okay? Where I live, sadly to say, is parts of Washington and our Canadian provinces to the north. Instead of having fire, we have logging trucks. But this process of succession is ubiquitous throughout ecosystems in nature. It happens in oceans. It happens from the surface of the ocean. Ramon Martellef would see his successions with plankton at the surface, zooplankton right underneath, and small fish underneath this, larger fish underneath this, and larger fish underneath. He saw a vertical succession. Early workers who worked in the lakes, in the Great Lakes region, would see a succession from the edge of the lake, and as you went further away from the lake, there'd be wind and da-da-da-da-da, and finally he'd get big trees here and small trees and shrubs here. So successions are very much a ubiquitous process. And what happens after the climax cars? Okay, let me just go back. And this is a little complicated, but we'll look at it. This is time in this direction. And we'll look at just two curves here initially. This is the biomass curve. Okay, now if we go out and measure the amount of biomass per square meter, it's pretty low. Cut it and weigh it, dry it, weigh it in the lab. We come back over time, now we're measuring the amount of biomass per square meter of an oak tree. It's pretty high. So over time, the one thing that happens is the amount of biomass goes up. PST is total system throughput. This is energy. How much energy is flowing through the system over time. When it's a grassland, not much energy is flowing through the system. But when it becomes a hickory forest or climax forest, there's lots of energy flowing through the system. The system diversity goes up over time. We'll look at that. This is very low diversity here in the grasslands, okay? And more diversity in the higher climax forest. So we can argue about this, but there's much higher diversity, for instance, in the Amazon. We look at it that way. And there's much lower diversity in the Arctic, okay? You can look at it on a global basis, but it turns out that diversity increases with more mature systems. Another one I have here because, and I'll just show it, and you'll see there's an immense amount of known about these systems. Because I come from forestry and cow country, this is the net production of the system. This is often right in here where we cut down our trees because they kind of grow as much as they're going to. And this is the time in my country where they grab the cows off the land and put them in a truck and take them to a feedlot because they've kind of grown as much as they're going to. Now the amount of data that ecologists have gathered on a ecosystem basis is staggering. The first person, the first ecologist to start really gathering and looking at data from successional processes was Thoreau. And he was wandering around the woods of New England 100 years after the Pilgrims and saw stone walls in the middle of the forest and looked at the ages of these things and realized that there were successions going on because these fields were of different ages and you could see things happening. And he wrote a paper for the Middlesex Agricultural Society in Massachusetts and first described successions as we know them. Now, what I want to do is we're going to look at the characteristics of ecosystems through growth and development. I hate these kind of list slides, but we're going to look at this very briefly. Over succession, they capture more energy. There's more biomass. There's more energy flow within the system. Look at this. They become more efficient in their use of energy. This is like with us, okay? As we grow older, we become more efficient in using our energy. And if we don't, okay, look at us. Okay, we eat more, we don't efficiently burn it off. There's more cycling of energy and materials. There's greater numbers of cycles. You'll wonder now how I know all this. There are longer cycles. Turnover time of cycles and cycling rate decreases. The amount of material leaking out of the system decreases. There are higher trophic levels. There are longer food chains. Greater trophic efficiencies. Higher interconnectivity and articulation between species. This is Bobby Lanover's report. Higher respiration and transpiration. Higher species diversity. These are the characteristics of a more mature system. Immense amount of that. They have cut down forests, looked at oil spills. They've done a zillion studies and the type of work to gather this type of data. Now, how do they do this? They go out in the field and they follow energy flow. They look at plants, we look at the detritus from plants, and we look at the bacteria that eat them, we look at the detritus from the bacteria, we look at carnivores, and we look at all the energy flows between these systems. Okay, now how do we do that? We're just going to take a really simple animal, and we're going to put him in here as one of the animals in a food plant train like this. We take a rabbit. Okay? Rabbit has energy food in it. Okay? He has waste out. Okay? Now, imagine guys doing this with zooplankton. Okay? I've known people who have done this, 4 men who did this in the field for 3 years. They worked for Howard Oven, and after doing this, they haven't talked to one another. And you'll see why. Wait till I show you something really complicated. Okay? Then they also have to not only look at food in and food out, but then they got to look at other things that the rabbit does. Got to keep track of everything. And this is just the most simplest of systems. Okay? And then look at what else happens. So that'll look at the things that the rabbit leaves behind, etc. Now, what do they do with that data? I don't expect you to look at this because we're just going to trace fossils. We need to trace other things. This is a graph by Bob Ulanos at the University of Maryland. This is tracing, we'll just say energy flow. On the far left-hand side are plankton species. Okay. Here are bacteria, zooplankton, the things that eat these. Here are things that eat the zooplankton and things like that. Over here we have fish. Okay? These are their waste. These are their children. Imagine this. Okay? But with this type of data, okay, gathering this is unbelievable. Not enough of the data. There's clams. There's oysters. Okay? There's waste coming out, energy coming out. Gathering this type of data, we can calculate the total energy flow through this system. Okay? Total energy flow through this system, believe it or not, is exactly comparable to the gross national product of this system. And as a matter of fact, the mathematics they use to generate this is the exact form of mathematics that Leontief used to determine the gross national product of the country. He won the Nobel Prize for that. Okay? But we can also calculate the cycling of the system. We can calculate the waste of the system. We can calculate the trophic levels of the system. Okay? An immense amount of data can be calculated for this. For any of you that have colleges, students, etc., I strongly, and it's PhD work, I strongly suggest they go out and I don't care if they do it in a mud puddle or do it for the entire Yellowstone Park. I'm trying to get a study going for the park. But these types of things reveal so much data about ecosystems, and so few studies that have been done both on terrestrial and terrestrial aquatic or marine aquatic that it's shameful. This is, even though this looks complicated, and it is complicated and requires an immense amount of field work, it's highly worth doing. Now we're going to shift gears. We're going to look at another kind of energy flow. Now we've looked at carbon flow as it goes through all those things. Now we're going to look at energy flow from space. Here I have 9 different species of trees. What did we say? All of them are different, but all of them are the same. Sometimes you may see this tree and this tree and this tree in a clump in a hedgerow. But when you look at them, they all clump together and form a symmetrical shape. Now I promise you, once you walk out of this room and you look up at a tree, you'll never look at one differently. Okay? You're going to look up and see an energy collector. Okay? You will. You'll never look at a tree unless you look at one through these eyes before. Trees are built to collect energy. This is a chiffonnier plant that sits in my office. Where's the link? Now we're going to look at a tree in a different fashion. Here's a tree with 800 watts per square meter. Where does the energy go? It's getting 100, this is a 35, 40-foot tree. It gets 100 kilograms of water a day. 15% of the energy is reflected. 18% of the energy from the tree is given off heat. This is heat with heat comes off like a parking lot. This will shock some of you who aren't in biology. Only 1% of the energy is given into biomass, in the leaf, acorn, and bark of the tree. 66% of the tree is given off its latent energy, evapotranspiration. So most of the energy, a lot is reflected, some is turned to heat, but 66%, two-thirds of the energy coming in is evapotranspired. When you look at it when you look at a tree now, think of a tree as being a giant evaporator. You can't see it come, giant sprinkler in the middle of the field. Give me enough water, cooling. All of you've done this. You go and put a tent, bring a tent, put it out in the field. 2 o'clock in the afternoon, you want to take a nap. Call into the tent, it's 120 degrees. Okay? But if you put it under a tree or in a forest, it's nice and cool. Okay? Because this thing is evaporating water. The next time you look at a tree, look at it as a giant evaporating machine. There's an artist in our town, Russell Chatham, who's really, really good. When I gave this in a bookstore and showed this to Russ, to think of this thing as a big sprinkler out in the field doing this, he really kind of looked at me like I was crazy, but then when he saw what I was talking about, he said, that's really neat to think of it as a sprinkler that's giving Okay, now we're in space. North America, South America, Africa. This is the winter. Very cold. Blue is cold. Cold in the air. Forget the oceans. Ooh, look at this. Amazon's cold. Congo Basin is cold. Sumatra, Java is very cold. Rainforest, lots of trees, evaporating. These things are cooling the earth. Same process we saw on the neighborhood of a tree. It's taking place here in our rainforest. The other day, 3 weeks ago in Nature, there was an article, a lot of articles since it, those of you who read it. Amazon's drying up. Okay? Amazon's drying up. On the same page on Nature, there's an article. NASA almost figured out that their photographs were missing 60% of the trees that were being cut in the Amazon. And the Amazon was drying up. We're running water. This is a flight over Atlanta. Cool in the farmlands, hot over the cities. All these have black birds. That's why it's hot. We painted these blackbirds silver, and we could save $6 billion in air conditioning in the United States. Because I'm limited in time, this is the mid-ocean ridge. These are the hot spots underneath the oceans. This is where we've seen the crabs, the tube worms, the large clams. This is probably where many people think the origin of life is. Here we have a gradient, hot magma, reducing chemicals coming out of the plume, gradients between hot, cold ocean, between reducing chemicals and oxidating water. Good place for life. Gradients, making organization. Evolution in the frame of ecosystem development. G.L. and Evelyn Hutchinson, probably the leader of all ecology in America, wrote a book with the delicious title, The Ecological Theater of the Evolutionary Play. What was it telling us? Ramon Martellef, a magnificent Spanish ecologists. He said, succession is in progress everywhere, and evolution is encased in succession sprang. We saw before that succession has a direction, okay? And evolution is following in that direction. Marlowe gets a little more poetic about this. So evolution cannot be understood except in the framework of ecosystems. By the natural process of succession, which is inherent in every ecosystem, evolution of species is pushed or sucked in the direction taken by succession. Now, I've been giving this reading for a while, and I've been looking at the directionality in my successions. Then I came back home after doing this, and written a book on this subject. Then picked up my Gould, I picked up my Mayer, and they said there is no direction in evolution. And there is no direction in evolution. And then I'm seeing people like this who I really admire who say evolution is being pushed or sucked in the direction of successions. Then I've shown everybody that successions have directions. Okay? I said, uh-oh, I got a problem. Now let's look at evolution. This is the Cambrian, this is the Triassic, 600 million years ago. In this case, I've got the number of genera. One thing we do know, even if this was species, this was zero at this time. Right now, this is about 10 million species. The history of species have had, as you can see, its ups and downs over geologic time. This is a giant drop. We really don't know what happened at the Permian and Triassic boundary. This we think was an asteroid. This is where the dinosaurs were now. But one thing we do know is after these events, the number of species climbed, just like after my successions. After it went down, the number of species climbed. It came back time and time again. But the one story is the numbers, there was a direction here. Planck and Agee would disagree. There's a direction in the number of genera at the time. This is an amazing data set. It comes from Russia, but I've really convinced this set. On this axis is time, and on this axis is metabolic intensity. And what he's done, these are the various species, from cellularites, mollusks, clear up to hummingbirds. I've actually plotted man, an American man, sits up in here. Okay? So we are using energy at a higher and higher intensity. And over geologic time, there's been an increase in energy intensity or energy metabolic rate over time. There's another piece of evidence looking at a time vector, change in time, a direction over evolutionary time. Now right now, this is where I'm looking. I know I'm going to find an increase in efficiency over time. There's a whole series of relationships that exist between the variables like metabolic intensity, efficiency, etc. that people have found down at the Santa Fe Institute that show similar things. Now I'm going to jump here and just finish with one last thing. When I was writing this book, people came to me from various areas of science and wanted their stuff put in the book. And this was one of the things that I put in that was different than most. At the age of 30, as human beings, time, at the age of 30, nothing we can do about it. This is normal aging. All of us start to lose our vitality. And this is measured by VOX, by looking at our metabolic capacity. Okay? All of us lose this at 1% a year, moderate activity. If we want to be a super athlete, and we'll show you what that means in a moment, you can slow that down to 0.5% a year. If you're sedentary and a couch potato, you lose it at about 2% a year. We have various diseases that can knock it down even more. So let's just look at that. And we're going to get to think about this in a moment, what this means to people, couch potato and moderate activity. This starts at 30 years. You really can do nothing about it. This is the normal process of aging. We all basically go down about 1%. Some of us at 2%. And they're really good athletes. And I see a few of you in the room go down at a 0.5% a year. And now we're going to do an experiment. And now we're going to go 20 years in the future. Okay? The moderate activity is aging at his normal rate. So he started at 30 years, and now it's 20 years later, he's 50 years old, where he ought to be. The super athlete, he's aged at a slower rate, he's equal to 40 years old. But look where a couch potato is. He's equal to someone 70 years old. Do you want me to run this slide again, or do you get it? So, this is energy plus stuff. This is mu-x max, frailty, vitality. Okay, how much is enough? This is how much food you eat. This is your activity level. This is your anabolic yield level. Some people, and we know them, who are super athletes, work out so well and finally are burning their muscles and everything, and are ragged. Good marathoners really only have 10 marathons in their body, and then they're using it and losing it. They're running off their anabolic yield. You use it and lose it, people are the couch potatoes, and they're running off here. So what's the level of activity? Everybody wants to know, how much should I work out? When I wrote the book, the guys I know told me 2,500 calories a week. That's 500 calorie a day workouts. That's a lot of workouts. That's a lot of work. Since then, and literally within 3 months of this coming out, two of my friends, Walter Bortz and Gene Yates, both of them who are in this area, got the book, went down to the UCLA medical school and started working on this number and flattening the curve. And they suggest now that I put this at about 1,800 calories per week. That's fine. One last thing. If we're going to have a sustainable planet, how would we like to live? The one thing we like to do is live like an ecosystem. We'd like to have optimum energy throughput, like our GMP. Optimum sustainable energy capture. Don't forget that word. Maximal energy efficiency. Again, this is living like an ecosystem. Low rates of cycling and recycling. Material and energy should be kept in the system. Maintain the diversity of the system. Maintain compact hierarchies. Maintain sustainable population. Recycle waste. So these are how ecosystems maintain themselves over a long time. Perhaps when the plants can learn something from. That's it. Okay, now I'm going to turn this over to Dorian. Other questions? Yes, we have some time for questions. Because I'm not the timekeeper here. Okay? Questions? Whatever the room will do a lot of stuff.
I'm looking on evolutionary biologists myself, but my understanding when evolutionary biologists say there's no directionality, all they mean is that at any one time, organisms could evolve to be larger and some will evolve to be smaller. Some will evolve to have a higher metabolic intensity or a lower. So over time, of course, the largest organism is going to be larger. But there's no directionality in the sense that there's no drive or any plan or anything that would necessarily make organisms get bigger or more energy efficient.
Except the more efficient organism will have the hands up on the less efficient organism. Okay?
Not necessarily. Depends on the niche that
In general.
I would say in general, the more efficient organism. If you take, let's say you have 5 little companies in town that run bicycle delivery services, okay? And one of them is more efficient in delivering his service a 5 minute faster than everybody else. He's going to be the one that survives, okay? Now, you're right, in individual niches, sometimes there's a reason, there's a good reason to be smaller, okay? If you're a hummingbird, or as I see wrens around my house, it's good to be able to fly in that little hole. And if you're a robin, you're not going to make it in that niche. So there's no reason, it's not any good to be a big animal and fit into that niche. But in generally, there's some vectors, like efficiency happens to be one of them, that you will be selected for rather than the less efficient. I believe.
It's really the
I just want to
ecosystem.
mention one word, cockroaches. How long have cockroaches been around? Long, long time. Are they efficient? I would say that cockroaches were very efficient and lead a long geological time life. So I think that's probably an example of your efficiency organism.
Yes,
Cockroaches will inherit the earth.
and they will. That was good bacteria.
Yeah, that too.
Can I just make one comment on the direction thing, because I think it's there's sort of the system versus the individual things, and I think there's nothing, I mean, individual things can go in any direction at all, but I take it that one of the things you're pointing out in terms of directionality is system directionality. There's going to be a lot of things going on in between, but the question is, does a classical model expect this growth in the ability of the system to perform work, which I put it, Lovelock put it that way, I like that way, and just say that there's really no expectation that this system would be going that way from it, because classical Darwinian, neo-Darwinian really doesn't talk about energy flows or energy as an issue for them, except survival are the ones that are, I grab the energy more than you do. The idea that the system will actually expand and grow and become more efficient and more powerful is an unexpected empirical data.
Stephen Jay Gould saying that if you rerun the system, you'd never get anything like intelligence or humanity to re-evolve, but then you compare that with his placement of humanity at the top of that energy efficiency graph, and it seems like that's another kind of mismatch that's going on with regard to orthodox and non-progressive evolution versus this thermodynamic view.
Thermodynamics, and the sun is always coming, there's always energy coming up, and it's piling up on the Earth. Okay? And this gives evolution a push. Okay? It gives evolution a direction. Other questions? Okay, Dorian's going to come up here, and if you think I was provocative,
We have a little time.
if you think I was provocative,
We got about 10 minutes.
I'll give them more. Because we have no one coming in after us.
But these guys have to go places too.
But if you